Okay, our next presenter is Harneet Grewal from the Department of Physics. And Mr. Grewal is going to present, as you can see from the title page, reflectivity test on the Class 12 high threshold Cherenkov counter mirror assembly located at the Jefferson Lab. So let's get started. I'll put up a little flag if you want to be comfortable and entertain us.
Well, Cal State Dominguez Hills is part of an international collaboration which Eddie briefly touched on called CLASS. The centerpiece of this collaboration is the Class 12 detector. For the last 3 years, through the Department of Energy, I've been working on a group located in Virginia which is designing and constructing the mirror assembly which is going to go into one part of the detector called the high threshold Cherenkov counter. The purpose of this counter is to allow us to differentiate between electrons and pions between that critical momentum range of 2.9 GeV to 4.9 GeV. Today, I'm going to discuss about the work which I specifically did over the summer. The experimental proposal for Class 12 requires such a great amount of efficiency that the mirror reflectivity has become a critical parameter. And so this summer, with the Department of Energy, I sent out back to Virginia to develop a test from the ground up, from scratch, to accurately vet the reflectivity of these mirrors and make sure that they're up to specs and in line with our simulations. So here's an example of one of the mirror segments. These are built at the lab. The actual mirroring of it is going to be sent out. This was the first reason why we did this experiment, was because we had to vet potential vendors. So the challenge which I was given, myself, under the supervision of a staff scientist, basically I walked in the lab and he gave me this used gear and said, create an optic bench out of this. That's what we did. That's right. And the goal was to do it within budget, without buying anything new. So what we did is secure a monochromator, which is going to simulate the Cherenkov light, using a beam splitter, which will send one beam to a controlled photodiode. The other one goes for a mirror sample and then gets read by this experimental photodiode. The reason for the control diode is because we quickly figured out that the intensity from the monochromator was not constant. So in order to remove the data analysis, once we eventually get our data, we put a control diode. And here's what it looks like in action. Just an optic reel here. Beam splitter is here. Actually, this one is reversed from that diagram, but it's essentially the same. The control diode is here, and here is the experimental diode. This is a XY translation gimbal, which is where the actual mirror sample goes. Now, with this setup, one of the challenges was aligning it. Once again, because reflectivity was such a critical parameter, alignment was a problem. Now, this is a laser which we were originally going to use to align the optical bench, but I quickly figured out that at the Department of Energy, they don't like us to use this laser. If we were going to do this, it would have required a PhD staff scientist to supervise and require at least 4 weeks of paperwork. This was not going to work. So the first challenge I was given is, well, if we had a laser pointer, which is basically nothing more than a cat toy. This did not violate any safety problems at the lab. How can we get this cat toy to accomplish the same type of precision alignment as this laser will? So of course, as physicists, we start taking stuff apart, and I removed the top of the monochromator. The idea is, if we can place the laser beam in the direct path of where the monochromator is, we should be able to get the same kind of precision alignment. Of course, the challenge was, how do you mount a laser which has to, in a sense, float in the beam line? So we created this, one of the technicians made this plexiglass plate. It's difficult to tell here, but this supplements the cover, and we put the cat laser pointer on these 2 screws, which gives us X, Y, and Z translation. So even though the laser itself, we don't know the accuracy of it, because we can control its mounting, we were able to achieve the same amount of alignment as we could have with that fancy laser and avoid stacks of paperwork. And here's another example of it. And there is it being set. We're doing the alignment procedure here. And here you can tell, it's difficult to see here, but you can see we were able to achieve the same amount of accuracy. And the best thing is each time we could commit that the alignment was exactly the same, even if we moved stuff around. The next problem we have is light contamination. The staff scientist who was in the sense my boss went to a conference and said, I'm going to be back in a week, figure out how to get light out of the box. The original design which he had put the monochromator inside of the light-tight environment. We did not anticipate that the monochromator leaked light, which made it difficult to have inside of the box. So this was the first idea, to wrap the monochromator in a black blanket and then place the box over it, which had the result of overheating and destroyed the bulb. Fortunately, before Dr. Puckett came back, I started experimenting with another idea. If we could somehow remove the monochromator from the light-tight environment, get it out of the box, yet still be able to direct a collimated beam of UV light into our test bed. This was the first rough sample, and then this was a styrofoam prototype which I made just out with an X-Acto knife to give to one of the technicians to actually machine. The end result was this: a docking collar which sits flush with one of the black boards, which allows us to now mount the monochromator in one set position so it doesn't move, align the whole setup without the light-tight box. Then once we're ready to do experiments, the design of this is a better view of it, we made this docking collar, which in a sense securely, snugly fits with the light port, which allows the beam to come in. The end result is we got the monochromator outside of the black box. The reason why this was important is because, like I said before, the tolerances which we're dealing with were so extreme. In fact, the light-tight environment from our pico ammeter was, our noise level was 0.2000 pico ammeter, so there was no light in there. And this accomplished it. So then we finally got to be able to do the actual experiment. And this is the preliminary data which I've secured, actually, and which is a good example which you can see how precise our measurements have to be. Like I said before, the mirroring is going to be outsourced. One of the things we needed to do is give a recommendation to the HPCC committee on what vendor to use. Because the Department of Energy requires that you get at least 3 bids. So we got 3 bids from 3 different companies. Let me explain this graph really quick. This is the corrected one, so I'll stick with this, with the error analysis. Of course, the black represents our control mirror. ECI coating and AGC were both silicon dioxide coatings. And as you can see, the reflectivity between the two, the difference between it was quite light. And actually, the purple one here is our simulation data. And this is all cross-referenced with the actual simulation which they ran before we began designing this thing. So the end result of this is, it's actually, I've been working on this project for 3 years, starting from here on campus to actually building the mirrors to now the final step where we're actually putting the silver on the mirrors. Hopefully next time I go there, I'll be in actually working there on the actual detector. And the experiment was a success. Thank you.